Okay, so at this point, if you've had your fill and don't want to go through the numerical example, you can feel free to stop. You won't be losing anything. However, if you're okay with math, it doesn't scare you or intimidate you, I would encourage you to get the PowerPoint out and follow me as I go through this, because you'll understand the Walrasian system a lot better if we work through a simple example. Okay, so this is going to be quite simple. There's going to be two consumers, Xavier and Yolinda, and I picked those names, of course, because of the X and Y. So Xavier starts with 24 apples and Yolinda starts with 8 bananas. So Xavier's utility function, utility to Xavier, that's what the X is equal to the natural logarithm, so just ln, or what people might say ln, the natural logarithm of ax plus the natural logarithm of bx. So what that's saying is Xavier, once he completes his transactions and he has however many apples and bananas he's going to eat, so ax is the number of apples Xavier eats, bx is the number of bananas Xavier eats, you compute the number of utils that consumption yields him by taking the natural log of the A plus the natural log of the B. Okay. Yolinda, quite similar, just you have Y's as the subscripts instead of X's. Okay, so what is the equilibrium now in this simple example of what we might call a pure endowment exchange economy? All right, so it's just pure endowment, meaning they just start with goods. There's no production. There's no saving and carrying things forward into a future time period. It's one shot. They start out with a distribution of goods, and they have the option of trading, right? So we're going to see they're both going to be better off by trading than if they just consumed what they originally started with. One last note. I am going to designate apples as the numeraire commodity. And so I could have picked bananas, but given that there's just two commodities, apples and bananas, it will be easier mathematically if we just by definition say one of the prices is 1. We don't need to do that. We could have the prices of apples and bananas be both different from 1, but all the Walrasian framework really gives us, the approach really gives us, is we're going to pin down in equilibrium what is the exchange rate of apples for bananas, or vice versa. And so we can scale the prices up or down. If we found out, for example, that one apple trades for 2 bananas, we can say, okay, apple price is 1 and the banana price is 1/2, right? So one apple trades for 2 bananas. Or we could say the apple price is 6 and the banana price is 3. And that wouldn't change the equilibrium. You might say, well, those are different prices, but no, all we're really pinning down with the Walrasian approach is the real exchange ratio. All right, so this goes back to what I was saying before about how economists in this tradition tend to think of things as, they think like marginal utility and marginal productivity. What that pins down are real exchange ratios, barter exchange rates, if you will. And then when you want to figure out absolute money prices, you have to have a different theory to figure out what that price level is going to be. Let me try that one more time because this is a crucial point. People in the Walrasian tradition can pin down relative prices. So they know an apple trades for how many bananas, but then when you want to say what's the absolute price level, they would often resort to a completely different theoretical mechanism. And again, I'm anticipating Mises got rid of that. He solved that problem. So back to this simple example we're working with. Apple prices we're going to say are 1 by definition, and then P is going to be the banana price measured in apples. All right, so P is a variable. What we're trying to figure out is what does P have to be to give us equilibrium. And again, P stands for price. P is the price of a banana, but it's measured in apples. So if we find out that P is 2, what we're saying is apple prices are 1, and then banana prices are 2, meaning you have to give up 2 apples to get 1 banana. Okay, let's now talk about Xavier's optimization problem. in this framework. Okay, so Xavier, what does he want to do? He wants to maximize his utility function, taking the price P of bananas as given, and he thinks that he can buy as many apples or bananas as his budget allows at the stipulated price. All right, so what we're assuming is perfect competition. All right, so Xavier doesn't care how many bananas and apples there are in the economy. It's not like he knows, oh, wait a minute, there's actually only 8 bananas, so I can't buy more than... No, given what the price is, Xavier just assumes I can buy as many bananas at price P as I want, with the only constraint being my budget. Okay, so mathematically what he's doing is he's maximizing logarithm of AX plus logarithm of BX such that AX plus P times BX is less than or equal to 24. And so that's his budget constraint. That's such that thing. Because remember, apple prices are 1. So what we're looking at, the left-hand side of that inequality is how much he's spending. So whatever he ends up consuming of apples is going to cost him AX, and then however much he spends on bananas is going to cost him a total of P times BX, because bananas have a price P. And then he starts out with 24 apples. That's what the right-hand side is. All right, so again, think of it as his income in the beginning, or his budget, is 24 apples, and then he has to decide how to spend that on apples and bananas. So think of it as he sells his 24 apples into the marketplace, and then he might buy some of those apples right back. That's one way of thinking about it. Or you can equivalently think about it as he decides how many apples he wants to consume, and then whatever he has in terms of his endowment that's above that, he sells in order to then buy the bananas that he wants to consume. Okay, so now how do you solve that? Well, you can use calculus directly if you're comfortable with doing that, and just get a first-order necessary condition. You just take the derivative of that thing. You do some substitution, then take the derivative, set it to 0, and you get first-order conditions that pop out. Or you can use your economic intuition or insight and realize that when the consumer is optimizing, it must be the case that the marginal utility of apple consumption divided by the price of apples equals the marginal utility of banana consumption divided by the price of bananas. Right, so that's a familiar condition that must be true at any consumer optimum. So the intuition is, again, if you're thinking about it in terms of marginal utility being cardinal, you want to say, I want to, across all possible goods, if I'm in equilibrium as a consumer and I have a certain amount of dollars that I'm to work with, to spend, how do I maximize my utility given that I have these number of dollars to work with and I see these prices posted in the market? I want to adjust my quantities such that the marginal utility per additional increment of money spent on any particular good is equal across all goods. So if I were to spend epsilon dollars more on any particular good, I would be indifferent which good that I did that on. If there were differences, if the marginal utility per extra penny spent were higher on apples than on bananas, then I must not be at an optimum right now. I should slightly reduce how much I'm spending on bananas and slightly increase how much I'm spending on apples, if what I said were true. So the only way I don't want to reallocate my money is if the marginal utility per extra amount spent is equal across all goods. Okay, so if you exploit that insight, you can very easily, what you do is you figure out the marginal utility of apple consumption is pretty easy. It's just 1 over AX. That's why we chose the natural log. If you know calculus, you know the derivative of the natural log is just 1 over whatever the variable is. So that's why we picked those functions that might have struck you as odd. If you don't know what those things look like, well, probably this example is not going to be too meaningful to you. You can think of it as a square root, right? So if you can understand how the square root behaves, that as the number increases, the square root of it increases also, but the increment gets smaller and smaller. Natural log behaves the same way, but the derivative of the natural log is much neater than the derivative of the square root. Okay, so from all that, you can conclude that the optimizing apple consumption is 12, and the optimal banana consumption is 12 divided by P. Let me talk about this for a second. We have here derived Xavier's demand functions as a function of P in his original endowment. So what we're saying is whatever P is, Xavier always wants to consume 12 apples. And then how many bananas does he want to consume? Well, it's 12 divided by P. So bananas are variable. That depends on what P is. Apples is always 12. So really what he's doing, if you think about it, remember he starts out with 24 apples. Xavier runs his optimization problem, and he realizes for any banana price P, I'm going to consume half of my apples, and then I'm going to take the other half, sell them into the marketplace, and buy as many bananas as I can. So if you want to think of it like this, with this particular utility function, Xavier always wants to spend half of his wealth on apples and half of his wealth on bananas. In general, that's not going to be true. It happens to be true for this particular utility function. Okay, Yolinda, now that we spent so much time on Xavier, Yolinda's pretty quick. What's her optimization problem? She maximizes natural log of AY plus natural log of BY such that now her budget constraint's a little different. Her budget constraint says AY plus P times BY is less than or equal to 8P. Why is that 8P? Because remember, she starts out with 8 bananas. So when we want to figure out how much total wealth does she have measured in terms of the numeraire, it's not just 8, it's 8 times P. So we're measuring wealth in terms of apples. So Xavier's budget constraint had it in terms of 20, it just said 24, because he started with 24 apples. But Yolinda starts with 8 bananas, so the most she can spend is 8 times P. Okay, using similar logic as we did before, we can conclude that Yolinda, when she's optimizing for an arbitrary P, she wants to buy 4 P apples, and she will consume 4 bananas. So she did a similar thing. She took her initial endowment and then split it 50-50 in terms of market value between bananas and apples. So she started out with 8 bananas. She took half of it, namely 4 bananas, to consume in the form of bananas. She sold the other 4 into the marketplace and bought as many apples as she could with it. And so when she sells it in the marketplace, she gets 4 times P apples worth of wealth. And so how many apples can she buy with 4P wealth? Well, 4P, because apple prices are 1 by definition. Okay, now we've established what the demand functions are from Xavier and Yolinda based on an arbitrary P. Now we want to find, is there an equilibrium price P that equates the quantities supplied and demanded in the two markets? Or I guess technically you could think of it as one market, really, if you want. That it's the apple-banana market. Okay, so remember, we now know for any given P, which is the apple price of bananas, Xavier and Yolinda will optimize by choosing these quantities. Xavier always consumes 12 apples, and then 12 over P, 12 divided by P bananas. Yolinda buys 4 times P apples and then consumes 4 bananas. So is there a P now that's going to equate the quantities of apples supplied and demanded and bananas supplied and demanded? That happens when P is 3. So when the price is 3, Xavier wants to, let's look at the apple market. When the price is 3, Xavier wants to sell 12 apples. and Yolinda wants to buy 4 times 3, 12 apples. Okay, so that clears. Quantities supplied and demanded in the apple market is equal. Banana market. Xavier wants to buy 12 divided by P. That's 4 bananas. And we know that Yolinda wants to sell 4 bananas. So again, it clears. Now, let's look at what would happen if we were not in equilibrium. Suppose the price were 2, P were 2. We know that's too low, right? Because we know the equilibrium price is 3. So at P equals 2, that means bananas are too cheap. What ends up happening? There's an excess supply of 4 apples. Where am I getting that number from? Well, plug in P equals 2 and see what happens in the apple market. As always, Xavier wants to sell 12 apples because he doesn't care what the price of apples are. Or sorry, the price of bananas. He always sells half of his apples, namely 12. Yolinda wants to buy 4 times 2 is 8 apples. So that's why there's an excess supply of 4 apples. Xavier's trying to sell 12, but at this price, Yolinda only wants to buy 8. So there's an excess supply of 4 apples. On the other hand, in the banana market, Xavier wants to buy 12 divided by 2 is 6. But Yolinda, we know, always wants to just sell 4. So Xavier's trying to buy 2 more bananas than Yolinda wants to sell. So that's why there's an excess demand of 2 bananas. Okay. What now? Suppose the price were too high. Suppose the banana price were 4. So the apple market, again, Xavier trying to sell 12 apples. Yolinda now trying to buy 4 times 4 is 16 apples. So there's an excess demand of 4 apples. On the other hand, in the banana market, Xavier wants to buy 12 divided by 4 is 3. Yolinda wants to sell 4. So now there's an excess supply of 1 banana. Okay, now let me point out something called Walras's Law. So here what it's saying is if you knew the excess demand, and by the way, if there's an excess supply, that's just negative excess demand. If you know the excess demand in all but one of the markets, then you necessarily know what the excess demand has to be in that last market. So here, let me just show you the way this works for this very simple model we have, that for the P equals 2 example, the excess supply was 4 apples, and the excess demand was 2 bananas, but those actually have the same market value, and they're just opposite. Because at P equals 2, the excess demand there of those 2 bananas, that's actually saying market value excess demand of 4 apples, right? Because each banana there has a market value of 2 apples. So there's an excess supply of 4 apples and an excess demand in the banana market of 4 apples worth of bananas. So you see how the two cancel out, or they add up to 0 in the system as a whole. All right, because that's what's happening. If you know the excess demands in all but one of the markets, you know the whole system, it's got to sum to 0, so then that pins down what it has to be in that last market. Let's look at P equals 4 in that particular scenario. The excess demand we saw was 4 apples. The excess supply was 1 banana. But wait a minute, what's the market value of that 1 banana at this wrong price? Well, at P equals 4, 1 banana has a market value of 4 apples. So again, we see the excess demand cancels out the excess supply when we measure everything in terms of the numeraire. All right, so you may remember now, this is the last point we'll make here, and I'll wrap this up, the discussion we had of Say's Law, where we were saying that in a barter economy, you can't possibly have aggregate excess supply. That if you have excess supply in a bunch of markets, then there's got to be excess demand in that last market that counterbalances all of it. And so when you understand the Walrasian system, you can kind of see that logic, even though, of course, J.B. Say wasn't writing out a Walrasian system. And so that's the logic. You can see how there is a certain elegant sense in which, and notice this isn't an equilibrium statement, right? Those two things I just walked you through, when P was 2 and P was 4, those were not equilibrium prices. I was specifically illustrating what it would mean to not be in equilibrium, just so you could really fully understand what it means when you are in equilibrium. So when you are in equilibrium, the excess demand or supply is zero in each specific market, whereas outside of equilibrium, it's only true summed across all markets, but in any particular market, there could be positive or negative excess demand. So this is not merely an equilibrium phenomenon. If Walras's law holds even outside of equilibrium, even when you have, quote, wrong prices. And so one might interpret what Say was trying to say is that, you can't have, in the system as a whole, there be aggregate excess demand or aggregate excess supply. That it can't be the case that in all markets people are trying to bring too many goods and they can't sell them. That just doesn't make sense mathematically. And then if that is what you thought he meant, then somebody like John Stuart Mill would say, well, if one of the goods, though, one of the commodities is what we mean by money, you could mathematically have it where you have excess supply in all the other goods or all the other markets, and then you've got your excess demand just in that one market that's we're calling money, and that would make Walras's law hold. But yet, isn't that what the layperson means by saying everybody's trying to sell too much stuff and there's a glut of goods? That when people say there's a glut, in general, they don't mean also in the market to hold cash. In fact, they would say the opposite. They would say, there's a scarcity, there's a shortage of cash. Okay, so again, I'm not necessarily endorsing that interpretation of what J.B. Say was arguing. Obviously, Say didn't set up a Walrasian system. I'm just relating what we just studied back to that particular controversy, so hopefully it'll click with you and you can understand now the different perspectives. Okay, this was a long one. I hope you guys learned a lot. I will see you next time.